This is Part 3 of Lecture 2b for ECE 361, Probability for Engineers, Drexel University, Fall 2016. In Part 2 of this lecture, we covered counting principles. Now in Part 3, move on to Section 2.1 from the text. We'll be discussing random variables, their basic concepts. A random variable is a function, and that function maps each outcome of a random experiment to a real number. Recall from the first lecture we introduced the notion of a probability triple. That triple had three components: the sample space, which held the set of outcomes, the set of events, where each event was a subset of outcomes, and the probability, which assigns a number to each possible event. By the discrete probability law, for the case of a discrete experiment, we saw that it suffices to assign probabilities to each of the outcomes in omega. Now, we're simply taking that a step further, and we're making a mapping from the outcomes to the real numbers. So, whereas before, our sample space may have consisted of non-numerical outcomes, such as heads and tails, red, yellow, and green, boy and girl, now we're going to be assigning a number to each of those outcomes. There's really nothing more to it than that. But as we'll see, the benefit of assigning a number to outcomes is that it enables us to use the rules of arithmetic to modify or compute different probabilities more easily. But let's make sure we're clear on the notation. X is a function. Its domain is omega, the set of outcomes, and its range is the real numbers. It need not be restricted to the interval 0 to 1. The notation x of omega means, given the outcome omega, x of omega is the real number associated with that outcome. We have one such real number assigned to each outcome in the sample space. Finally, I will use the acronym RV throughout this lecture and in fact throughout the course to note random variable. Let's do some basic examples. Suppose our random experiment is a sequence of 5 tosses of a coin. We can define a variety of random variables for this experiment. For example, we might want to simply count the number of heads in the sequence. A second example is 2 rolls of a die. Here, the random variable could be the sum of the 2 rolls, the number of 6s, or the second roll's value raised to the 5th power. It's not clear why you want to do that, but the point is that there's nothing in the definition of a random variable that prevents it. Third, to be a little bit more pragmatic, consider the random experiment where a message is transmitted over an uncertain medium. The random variable could be the time needed to transmit the message, the number of symbols received in error, the random delay associated with delivering the message, etc. There's several main concepts related to random variables that we'll be going over. First, as we just said, a random variable is a real valued function of the outcome of the experiment. It follows that if I take a random variable and define a function on that random variable, I get another random variable. For example, if my random variable is x, the number of pips on the face of a die, and I define y as x squared, then y is itself random because x is random. Also, as we'll talk about in a future lecture, we can associate with each random variable certain averages of interest, where the term average is a way of weighting the different probabilities of each value that the random variable takes. 2 such most important averages are the mean and the variance of the random variable. We'll cover these later. Next, a random variable can be conditioned on an event, and a random variable can be conditioned on the value of another random variable. We'll see examples of this as we go ahead. And finally, there is a notion of independence of one random variable from an event or of a random variable from another random variable. And again, we'll make these notions more concrete as we go. Next, let's talk about some additional concepts related to random variables. First, random variables in general can take on a finite, countably infinite, or uncountably infinite set of values. Let's give some basic examples of each of these three types of random variables. We have a finite random variable when, for example, we're counting the number of pips on a die roll. In this case, the random variable takes on the values 1 through 6. We'll have a countably infinite number of values when our random variable is the number of coin flips required until we get a head on the coin. Here, the random variable might take the value 1, 2, 3, or any arbitrarily large integer, that is, the natural numbers. Finally, our random variable will take on an uncountably infinite set of possible values when, for example, the random experiment is to choose a real number uniformly at random from the interval 0 to 1. As we talked about in the first lecture, there is no one-to-one correspondence between these real numbers and the natural numbers, which is why we call this set uncountably infinite. As we also said in the first lecture, in this first part of the course, we're focusing on discrete random variables, by which we mean the set of values that the random variable takes is either, I should say finite here, not discrete, or countably infinite. So let's talk about a few concepts that are specific to discrete random variables. So, as we just talked about, a discrete random variable is a real valued function of the outcome of the random experiment that can take a finite or countably infinite number of values. This next point is fundamentally important, and we'll discuss this notion at some length. A discrete random variable has an associated probability mass function, abbreviated PMF, that gives the probability of each numerical value that the random variable can take. We'll make that definition clear in the next slide or two. Finally, reiterating another point that we made previously, a function of a discrete random variable defines another discrete random variable, whose probability mass function can be obtained from the probability mass function of the original. And we'll do some examples to illustrate that in the next couple lectures.